Yeah, okay. Well, thanks a lot, for the invitation and for the introduction. So yeah, I will be talking about quantum expanders. So the goal is to, first define what these objects are, and then explain how you can actually construct them, and more particularly how you can construct them in an optimal way when you do it at random. And then at the end, I would like to talk about like one example where these objects show up, which is in the context of quantum many-body systems. There are many like examples of cases where these objects are useful. So this will be one particular one. And okay, so the talk is going to be very much an overview talk. So I will be presenting a lot of things that are not at all like results of mine, but amongst the few things that will be actually results of mine. So it will be based on two works. So one with David Perez Garcia from 4 years ago, where our goal was really focused on the like understanding properties of quantum many-body systems, and the quantum expander part really came as a side product of this work. And then a more recent one with Pierre Youssef, where this time the goal was really to try and understand how we can construct these objects in the most general way possible. So yeah, don't hesitate to interrupt me if anything is not clear. I did promise to Job that I would get to the application part, so I have to arrive there, but still, this shouldn't prevent you from not stopping me. I can skip some parts in order to get to this final application part. Okay, so let's get started. And what I would like to do first is to recall, classically what expanders are, because this will somehow help us a bit understand where the quantum definition comes from and how it's motivated. So in a classical setting, when we are talking about expanders, so we are looking at graphs, so some graph G on n vertices, and usually we're assuming that this graph is regular. So we'll say that the graph is D regular if it has exactly D edges at each vertex. So there are several settings that you can look at, but let's say the simplest and most studied one is when this graph G is undirected. So these edges are not directed, and exactly D of them at each vertex of your graph. Then I will denote by A the adjacency matrix associated to this D regular graph. So I will normalize it so that it's actually a doubly stochastic matrix. And this adjacency matrix, it's nothing else than this n times n matrix that has as entry KL, the number of edges between vertices K and L, divided by D, the total number of edges at vertex K. And now, so I will denote by lambda 1 to lambda n the eigenvalues of this adjacency matrix A that I will order in a non-decreasing absolute value. So now the fact that our graph G is regular, it's very easy to see that, it implies that the largest eigenvalue of this adjacency matrix is always going to be 1, and with associated eigenvector, the uniform probability vector that I will denote U. So this vector, that's probability that puts weight 1 over n on each of the vertices of my graph G. Now, what I will define as being the spectral expansion parameter of my graph G is simply going to be the second largest eigenvalue of this adjacency matrix A. So maybe one very easy observation that will help us understand a bit what this second largest eigenvalue of A quantifies is to see that it actually quantifies like a distance between our graph G and the complete graph on n vertices. And this is because this parameter lambda of G, you can actually see it as being the largest eigenvalue of our adjacency matrix A minus the adjacency matrix associated to this complete graph that I denoted by J, which is the matrix that has entries 1 over n on like all entries equal to 1 over n. And indeed, this is because this matrix J is actually projecting everything onto the direction given by this uniform probability vector U. And also it has eigenvalue 1 associated to U, and then all the rest is 0. So this spectral expansion parameter lambda of G, it's nothing else than like measuring the distance of your graph G to the complete graph according to this distance measure, which is given by looking at the largest eigenvalue of the difference between the two associated adjacency matrices. Okay, so now that we have, yeah, sure.
Are we assuming the graph to be simple? Can the E of K, L value be greater than 1 as well?
Like no, sorry, can you repeat?
Can there be multiple edges between two vertices?
Yes, you can allow multiple edges, and in fact, I mean, in a more general way, you can allow like weighted edges. I mean, here I'm not really, I mean, in the end, you can really do what, I mean, in the end, you want that this matrix A is a doubly stochastic matrix. And so, I mean, it's not, yeah, I mean, you can really allow for very general things, multiple edges, self-edges, and even weights on your edges.
Okay, thank you.
Does it? Okay.
Yeah.
Yeah, I mean, it can be very, very general. I mean, even if I'm not entering so much into these details. Anyway, so now that we have defined what is the spectral expansion parameter, we can somehow, I mean, define, I mean, in a way that is not completely mathematically rigorous, but somehow it gives you an idea of what the object is. So what we'll call a classical expander. So we will say that if you have a graph G on n vertices, which is D-regular, you will say that it is an expander if it combines the two following properties. So on the one hand, you want this graph to be sparse. So you want this degree D to be very small compared to the degree n of the complete graph, so to this maximal possible degree. And you will want that it's at the same time spectrally expanding, so that this parameter lambda of T is small compared to 1, which means that this graph, from the point of view of this distance measure, is still close enough to the complete graph. So it's really, if you want like this definition, it's saying you want your graph G to be an economical version of this complete graph. And okay, why is it interesting? Because I mean, if you have an expander graph, I mean, one property that it will have that it will like exhibit fast mixing. So if you have a random walk which is supported on your graph G, then it will converge very fast to equilibrium, despite the fact that your graph is very sparse. And you can make this very quantitative of saying that for any like initial probability P that you start from on your n vertices, if you apply your transition matrix A q times to this probability vector, you will converge toward the uniform probability vector, and the distance between the two, say in one long distance, is always upper bounded by square root of n times this parameter lambda of G to the power q. So the smaller this parameter lambda of G, the faster this exponential convergence towards the uniform probability distribution. Okay, so that's somehow like the definition and the main, the primary interest of this kind of objects. So now I would like to understand, so how we can construct a quantum analog of this. So, I mean, the correspondence is going to be very simple, and actually what we're going to construct is the analog of the transition of this transition matrix associated to a regular graph. And okay, the dictionary is really straightforward. So in the classical world, we were manipulating probability vectors P and Rn. So in the quantum world, these are going to be density operators rho in Mn of C, so positive semi-definite n times n matrices that have trace 1. So in the classical setting, we were looking at transition matrices that were sending probability vectors onto probability vectors. So in the quantum setting, these are going to be quantum channels on n times n matrices that are sending density operators onto density operators. So these completely positive and trace preserving map on Mn. And finally, classically, we're looking at graphs G that had the property of being regular, so which at the level of the transition matrix A meant that they were leaving the uniform probability vector invariant. So for our quantum channel phi, this is going, the equivalent property is going to be that it's leaving the maximally mixed state, so the identity over n invariant, meaning that our quantum channel is actually unital. So okay, here we have the equivalent of the transition matrix associated to a regular graph. It's simply a unital quantum channel. Now, one thing that we haven't really said yet is what would be the analog of the degree. I mean, we've seen what is the analog of being regular, but not what is the analog of the degree of the graph. And the answer I'm going to give is that one possible analog for the degree of the graph is actually the cross rank of my unital quantum channel. So maybe let me just recall it to be sure that we're all on the same page. So if you have a completely positive map phi on n times n matrices, you can always write it in its so-called cross representation, which is a representation of the following form. So you write the action of phi on an n times n matrix X as the sum over I of some conjugations by some operators Ki, where these operators Ki are called the cross operators of my CP map phi. And now the smallest d that you can find, so that you can write the action of phi in this way, is what we're going to call the cross rank of my quantum channel phi. And for a CP map that acts on n times n matrices, this cross rank is always at most n squared, okay, and potentially less than this. Just one last comment, because it's going to be useful for later. So on this expression, the way you see the condition that my CP map preserves the trace is by imposing that the sum over I of the Ki star Ki is equal to the identity. And the dual condition that my CP map phi is unital is given by the joint constraints that the sum over I of the Ki star is equal to the identity. Okay, so now that we have redefined exactly what is this cross rank of a quantum channel, what I'm claiming is that in the quantum setting, the analog of the degree of the graph is actually going to be the cross rank of my quantum channel. And maybe one way of justifying this is that it's easy to see that the two quantities, so the degree and the cross rank, actually quantify the same thing, and namely how much your dynamics can spread in one iteration. So what I mean by this is that, so if you have a D regular graph, and imagine you start from a probability distribution which is supported on just one vertex, so it's a Dirac mass on one of your vertices. Then if you apply your adjacency matrix A just once to this probability distribution, the support will be at most D. There are at most cross rank D, and you start from a pure state, so a density operator that has rank 1, and you apply your map phi to this density operator rho once, and then you will have that the rank of the output is going to be always at most D. And this output can be the mixture of at most D pure states. So the two things are somehow quantifying the same thing. Okay.
Yeah. You cut out for just a second. About 20
okay,
seconds.
Sure. Oh, I'm sorry about this. You want me to come back somewhere?
I think it's all still clear. I mean, your slides are clear, so I just wanted to.
Okay. Okay. Yeah. So just a recap of this slide. So we have the analog of the transition matrix associated to a D regular graph is going to be a unital quantum channel with cross rank at most D. Okay, so this is going to be really our quantum analog. And now we can really very straightforwardly define what we will call a quantum expander. So we will have such a unital quantum channel phi with cross rank D on n times n matrices. We'll denote by lambda 1 to lambda n squared eigenvalues that we will order in non-increasing modulus. As we've already explained, so the fact that phi is unital, it implies that its largest eigenvalue is 1 with associated eigenstate, the maximally mixed state. And we will define its spectral expansion parameter as being simply its second largest eigenvalue. Again, exactly as in the classical case, we can view this spectral expansion parameter as measuring the distance of our quantum channel phi to a particular quantum channel, which is the so-called maximally mixing channel. So the channel that I've denoted by pi that sends everything onto the maximally mixed state. And now we can again define what we will call a quantum expander. So if you have a quantum channel phi on n times n matrices with cross rank D, we'll say that it's an expander if it combines again two kind of seemingly incompatible properties of having a small cross rank. So it has cross rank D very small compared to n squared, the maximal possible cross rank, which is also the cross rank of this maximally mixing channel. But at the same time, even if it has this very small cross rank, it is close in this sense to the maximally mixing channel because it has a spectral expansion parameter which is small compared to 1. And again, I create the same interest for this kind of object as in the classical case. So you have this economical version of the maximally mixing channel, that exhibits, I mean, a dynamics that is converging very fast to the maximally mixed state. So with the same kind of quantitative estimate that for any initial state row that you start from, if you apply your channel phi q times to this state row, it's going to converge towards the maximally mixed state. And the one norm distance between the two is going to be upper bounded by square root of n times this parameter lambda of phi to the power q. So exactly a complete analogy with the classical set. Is everything clear about the definition of the objects, or are there any questions at this point?
Just to clarify, so when you talk about eigenvalues of the channel, you mean that you treat it as a linear operator and you vectorize the states that it acts?
Yes, exactly. And in fact, I mean, in many proofs, when we want to study the spectrum of these objects, it's actually, usually much simpler to actually view it as a matrix on Mn tensor Mn. Like to really somehow vectorize everything. But yes, so it's exactly what I mean by this. Okay, so if there are no more questions, I will continue. And now, come to, okay, how do these objects exist? Like, because it's like this, and what's the best you can do if you want to, somehow simultaneously have things that are sparse and resembling something that is very, very mixing. So again, I will start with a very brief recap of, what is known in the classical case, because classically it's really a problem that's been studied for much longer than quantumly, and where really, a lot of things are already very well known, and it's somehow giving us like an idea of what's the ultimate goal that we could achieve also in the quantum case. So classically, first, it's known that if you have a d-regular graph, it cannot be, there is a lower bound on how much expanding it can be. And the lower bound is as follows. So if you have G, a d-regular graph on n vertices, you know that this second largest eigenvalue of the associated adjacency matrix is always going to be lower bounded by 2 times square root of d minus 1 over d minus some quantity that goes to 0 as n grows. So that's the best you can actually achieve. And people have called Ramanujan graphs that would actually achieve this lower bound for the spectral expansion parameter. Of course, first question you can ask is, so do Ramanujan graphs actually exist? And there's been a lot of work around this question. So first, people have shown that, that there are explicit constructions of exact Ramanujan graphs, but only for some specific values of d. So namely when d is a prime power plus 1. So in these cases, you have like explicit constructions based on KD graphs of groups usually that achieve this. Then it's also been shown that there are random constructions of almost Ramanujan graphs for all degree d. And this I will come back on it later because it's really going to be the focus of all my talk, then also in the quantum case. And very recently, it's been, quite recently, it's been shown in a breakthrough results that actually, so Ramanujan graphs exist for all d, even if you're not necessarily able to exhibit an explicit example. So let me just come back on this point too about random constructions, because there's actually something stronger that you can say, and namely that so when n is large, in fact, if you want, almost all regular graphs are almost Ramanujan, and in the sense of the result that is stated here, which is initially due to Friedman, and the result is as follows. So imagine you fix your degree d, and then you pick g uniformly distributed on the set of all d regular graphs on n vertices. And then what you can show is that so for any error epsilon that you fix, with probability going to 1 as n grows, the parameter lambda of g of this uniformly distributed graph g is going to be upper bounded by 2 times square root of d minus 1 over d, so the optimal value, plus the small error epsilon. Okay, so this is really, a very strong statement saying that, so if you pick a graph according to this uniform measure, then for large n, almost all of them are almost achieving this lower bound 2 times square root of d minus 1 over d. So maybe just one comment, because it's something that will be useful later on. So this result, initially, it was not proven directly for like this kind of abstract measure, which is the uniform measure on the set of all the irregular graphs. It was proven for a much simpler and more concrete random model of regular graph, which is the so-called permutation model. So the way this model is defined is, so if D is even, then what you're going to do is you're going to pick permutations, sigma 1 to sigma D over 2, permutations of n element that you pick independently from each other and uniformly distributed. And then you look at the random graph that has as edges, so all the edges between vertex k and vertex sigma I of k, and between vertex k and vertex sigma I minus 1 of k. So by construction, you have something which is a random graph, which is irregular. And for this concrete model, people could prove a result of this kind, and then somehow extended it to this more abstract, like uniform measure on the set of all irregular graphs. So that's the first comment I wanted to make. And second one is that, so here the initial result was really proven, like where we're fixing your degree D and then making the size of your graph grow to infinity. And there's been like series of works to try and improve this to allow somehow D and N to both grow, I mean, at whatever respective speed. And it's been proven that, okay, potentially up to losing this optimal constant 2 here, but so up, and then this result actually remains true for any degree dn that potentially grows with n. You have that with probability going to 1 as n grows, this parameter lambda of g is of order 1 over square root dn. So this order of magnitude is true even for a degree that potentially grows with n. Okay, so that's basically what is known. I mean, there are a lot of other results around, but what is known and is like somehow maybe the main result in the simple setting of undirected graphs that we have in the classical case. So now let's try to understand in the quantum case and then what we can do and what we still cannot do. So the first observation is that also in the quantum case, there is a lower bound on how much expanding a quantum channel can be. So it's known that if you have a unital quantum channel phi with cross rank D, then there is a lower bound on its second largest eigenvalue, which is also of order 1 over square root of D minus some quantity that goes to 0 as n goes. So it's not really known like what would be the optimal value here. I mean, it also depends a bit on which class of channel you're restricting yourself to, but for sure there are some values that have been proven, but without really any guess that they would be optimal. But there are some values here that are not. So I mean, what we will call in this case, I mean, an optimal expander is a unital quantum channel that achieves this order of magnitude of 1 over square root of t for its second largest eigenvalue. Okay, so where you have an upper bound of the following form for the spectral expansion parameter of your channel phi. So again, first question, I mean, do optimal quantum expanders exist? And the first attempts that people made at exhibiting constructions of quantum expanders, so they try to really, I mean, exhibit explicit construction that were really like done by somehow embedding the classical optimal constructions of classical expanders into a quantum channel. And all these constructions were at the point that they were not optimal. So you were actually getting something that was like with few cross operators and a large spectral gap, but not achieving this bound of order 1 over square root of t. So you could think, okay, if we cannot exhibit explicit examples, can we say something about random ones? And okay, so one question is, how would you sample a unital quantum channel at random? And I mean, how would you do it in a way that is like where afterwards you can like understand from a mathematical point of view what is going on? Because like saying, okay, I will sample uniformly distributed unital quantum channel over the set of quantum channels that have cross rank at most t, I mean, it's not really something that you can analyze directly afterwards. And an idea for much simpler model of a random quantum channel would be to say, okay, let's pick the cross operators k1 to kd at random, under the two constraints, the two normalization constraints, that the sum over I of the ki star ki is equal to the identity, so that the corresponding CP map is trace preserving, and the dual one, the sum over I of the ki star is equal to the identity, so that the CP map is unital. And now, so I look at this random unital quantum channel that has these cross operators, and I can ask what is the second largest eigenvalue of this guy. And that's what Hastings did in a seminal work. And the model he looked at was a very simple one, where he said, okay, so which is really if you want, the quantum analog of this permutation model for graphs that I've presented you on the previous slide. So he said, okay, let's fix our cross rank D to be even, and then we pick U1 to UD/2, some independent hard unitaries. Then I set Ki to be so Ui divided by square root of D, so I renormalize things. And then I look at the random CP map file that has as cross operators all the Ki's and all the Ki stars. So I have D cross operators, where each time I have one operator and it's a joint appearing. So it's making the whole thing a bit nicer, because you have a map which is Hermitian, because you have both Ki's and Ki stars appearing. By construction, it's trace preserving and unital, because your cross operators are unitaries. And then he could prove the exact analog of the classical result, namely that for any error epsilon that you fix, with probability going to 1 as n grows, the second largest eigenvalue of this random unital quantum channel is going to be upper bounded by 2 times square root of d minus 1 over d plus this a recipe on how to. So if you have an optimal classical expander, then you can construct an optimal quantum expander at random from it. So you really have this recipe for how to do it, where the adjacency matrix of your optimal classical expander is simply giving you the variance profile of the cross operator that you're going to sample. Then you just sample D of them, and you have something which is an optimal quantum expander. And okay, one really interesting, one interest of this result is that it's telling you that actually you can obtain optimal quantum expanders from cross operators, which are very sparse. I mean, this variance profile here can have a lot of zeros, and with basically, I mean, any distribution, if until it follows this assumption on the growth of x1. Okay, so it's so this phenomenon of being an optimal quantum expander is actually a very general. Good. Are there any questions? Yeah.
This beta parameter, like, is it any constants, any positive constants that it holds, or how is it?
Okay, so I'm not completely sure. You're asking about this parameter beta. So I mean, okay, this constant here, the C double prime, it depends on beta.
Okay, but the beta would be any constant, and then
yes, it can be anything, but it will. So I mean, okay, yeah, it's true. I mean, it will appear some at the end. I mean, of course, if you take beta equals 1000, it's not going to be the same as if it's 1. But so it appears here in the constant, and I forgot how it depends on beta.
Right.
But I mean, there is an explicit dependence on beta, and usually, I mean, the cases that you would be interested in are going to be, I mean, beta at most. I mean, okay, no, it depends, but I mean, in many cases, I mean, beta at most 2 or something like this is already covering a lot of distributions. But yeah, and maybe so one thing I should also mention here, that so here I've stated, I mean, we've stated the result just on average. Of course, I mean, if you want to say a bit more, that somehow when things hold with probability at least 1/2 or something like this, I mean, you will have to make some extra assumptions. But I mean, then you just need to be able to compute variances in the same way that you are able to compute expectations if you want. And I mean, you can do it with a bit. We haven't done it in the paper because it was, and again, I mean, if you have much more specific distributions where you know much more, and in particular, say if you're in a sub-Gaussian case, probably you can prove much stronger concentration results, like the ones that are here, that things really are with probability very close to 1, actually holding. But this we didn't really do it.
Yeah. Do you think the independence assumption on the entries can be relaxed as well?
Yes, completely. Actually, I mean, and that's actually one thing I'm doing right now. I mean, to be able to, because the thing that this result here is not encompassing it's not so it's recovering this result with Gaussian matrices, but it's not recovering a result where you take as cross operators hard distributed unit rates, for instance, because the entries are not independent. And this is really something that, I mean, we did for simplicity to have this very general, like to be able to deal with this very general thing. But one thing I'm looking at the moment is really to look at, I mean, you take unitary cross operators with some assumption on their moments, and again, I mean, things work. I mean, it's really not so crucial the independence of the entries. It was just a commodity for us.
Thanks.
Yeah, so in fact, so I think, I mean, I had one slide about the proof that I will skip. I mean, if some people are interested in a bit more, I mean, I'm really happy to say afterwards, but since I really promised that I would talk about implications for MPS, I mean, I'm going to jump to this. And I mean, I'm very happy to take just a few minutes afterwards to give you just a few pointers at what's going on in the proof. Okay, but if there are more questions on the results, I can answer them now or later in minutes. Okay, then let's. Sorry.
Are there any explicit constructions already, or are all?
No, that's the thing, that for now all explicit constructions are, I mean, there are explicit constructions, but they are not optimal. Like you reach something which is, I mean, 1 over some power of d, but not 1/2. Because somehow, like, even if you start from an optimal, like, classical construction, the way you somehow embed it into a quantum one, I mean, all the attempts that were made, I mean, there's been a lot of work, I mean, like, by Aaron Harrow, by Jens Eisert and David Gross, a very seminal one by Andrews and Bainis and Adam Smith, and you somehow you lose something on the way, and you don't keep something like this quantum object which has this optimal spectral gap. And yeah, maybe, I mean, one thing that I can say now, I mean, if you want this result is like one first step towards the randomization, because it's basically telling us that if you take your cross operators as being sparse matrices and whose non-zero coefficients are just plus minus one, random plus minus one entries, and you will have something which, at least on average, is an optimal quantum expander. And so you need an amount of randomness which is much less than if you have to take a full Gaussian matrix or a full Haar unitary, but it's still random. Okay, so in the few minutes that I have left, let me tell you a bit like how these quantum expanders show up when you want to study matrix product states. So let me start, I mean, first with like going a bit what these matrix product states are and why they are interesting. So I mean, as you all know, I mean, one of the problems in practice when you're dealing with many body quantum systems is that the dimension of your system grows exponentially with the number of subsystems. So it can be a problem if you want to actually parameterize the set of states in this big exponentially large Hilbert space. But however, it's also known that in many contexts, I mean, the states of many body quantum systems that are actually physically relevant, and I will come back in a second on what I mean by this, are often well approximated by much more and a small subset of this global state space, which is the subset of so-called tensor network states. And the simplest example of a tensor network state is what we call a matrix product state, or MPS, and it's defined as follows. So an MPS on CD tensor M is going to be a pure state that can be written in the following form. So each of its coefficient in some product orthonormal basis is going to be given by the trace of a product of matrices, hence the name matrix product state. So you have here these matrices KIL that appear in this product, which are matrices of some size n. So this n is a parameter in your construction. And what's the interest of this family of states? Well, if you look at it, you see that the number of parameters that you need in order to describe such a state is simply m times d times n squared. So if this parameter m is fixed, it's a number of parameters that is linear and not exponential in n. And in fact, even if you allow, say, this n to grow, if it grows polynomially with m, you have still gained something because you will have a number of parameters here that is polynomial in m and not exponential. Okay, so it's a family of states that is really efficiently parameterized. Just a bit of vocabulary. So in this setting, we'll call the parameter d the physical dimension, because our physical state chi lives in CD tensor M, and n, this parameter n, is going to be called the bond dimension. It only appears in the construction, but not as a physical dimension ultimately. Okay, so why are these MPS interesting? Well, because it's known that if you look at 1D systems, so what I mean by this is that your M subsystems are disposed on the line, and then you look at gapped local Hamiltonians on this 1D system. So what I mean by local is that the Hamiltonian is composed of terms that will act non-trivially only on nearby sites. So there are no direct interactions between sites that are far away from each other in this chain. The fact that it's gapped, it means that I have a spectral gap between its ground energy and its first excited energy, which is lower bounded by some constant that is independent of m. So even when m grows, this spectral gap doesn't close to zero. So if I look at this gap local Hamiltonians, then there are ground states are well approximated by MPS. Okay, so that's really, I mean, that's a really important result. And it's, I mean, as a consequence of this, I mean, it's it has really a practical consequence, which is that in quantum physics, these MPS are really used constantly as ansatz in ground energy computation. So if you want to try and estimate the ground energy of your local Hamiltonian, you can perform your optimization over the subset of MPS, which means over a manageable number of parameters, even when M is large. Okay, so that's the interest of these matrix product states, at least one of them. And now that we have defined, so let me explain what we're going to be doing. So we're going to be looking at constructing this matrix product states at random, and then try to understand how correlations behave inside this matrix product state. So of random PS, or L here that appear in the product do not depend on the site I to N. Yep.
Sorry.
Oh, yeah, again.
Up for a second.
Yeah, so sorry, yes, so maybe I should so I mean,
Okay.
tell me when it stopped. So okay, what I was just saying, so now we're going to look at a very simple model of random MPS, where we're going to impose that the MPS is what we call translation invariant. So impose that all these matrices here actually do not depend on the site 1 to M where they are. So we will just have to pick D matrices K1 to KD to define our MPS, and we're going to pick them at random, okay? And look at this MPS chi in CD tensor M. So this corresponding random translation invariant MPS. So each of the coefficients of my MPS chi is going to be given by the trace of this product of M matrices picked amongst this set of D matrices K1 to KD. So if you like graphical notation, I mean, it's really not crucial for what follows, but you can really represent this in this vectorial way, where you have this, you have your one-site tensor K, which I've represented here, that gives an MN tensor CD. And then in order to construct my MPS, I'm actually contracting all these one-site tensors with one another on this N index. And I obtain this resulting vector in CD tensor M. I mean, this is really just for people who like this. I mean, there's really no need. I mean, you can also write everything with indices and be happy with it. And now one object that will be really important for us later on is the so-called transfer operator associated to this MPS. So the way you obtain this transfer operator is by taking your one-site tensor K, its complex, its conjugate K bar, and then you contract them on their physical index, so on this D-dimensional index, which I represented here on this diagram. And what you get is this transfer operator T, which is so the sum over I of the Ki tensor Ki bar. And these Ki's are my random matrices that I've picked to define my MPS. One crucial observation is that this transfer operator T is actually nothing else than the matrix version of a CP map that I've denoted phi T, which is the map whose cross operators are these matrices Ki. So the two things are really the same objects viewed either as a matrix, so a map that acts on Cn tensor Cn, or as content channel and a CP map that in spectrum. So the two objects have the same spectrum. Good. So now that we have defined what is going to be the model of random MPS that we're going to be looking at, let me explain briefly. So what I've said before. So what we're going to be interested in is to look at correlations inside this MPS. So again, this is something probably, I mean, a lot of you know, but just to be clear about what I mean. So we're going to be taking one side observables A and B. So observables acting just on one copy of CD. And then what I will do is I want to compare two quantities. So first I want to look at the value on my MPS chi of the following observables, where I have put observable A on site 1, then some identities on the Q following sites, then observable B, and then some identities on all the rest. So I'm computing the following inner product of this local observable here with my MPS chi. Okay, dividing by the norm squared of chi. In case it was not already normalized to be here, are separated by Q sites. And now I want to compare this quantity to the product of two quantities where, when I'm computing the value of the observable where I have only A, or the observable where I have only B, and do the product of these two things. And so we present it here on the right-hand side. And what I will define as being the amount of correlations in my MPS chi between observables A and B separated by Q sites is simply going to be the absolute value of the difference between these two quantities that I want to compare. And what we expect is that this correlation function should go to 0 when Q grows, because I mean, in this MPS, if you want, the correlations are just mediated from nearby site to nearby site through this product or this tensor contraction. And so if you look at two distant sites in this chain, they should be very little correlated. And we would like to make this quantitative to understand what is the speed at which these correlations decay. So one really very simple but key observation that this correlation function, before we had defined it as being something that we define as a difference between inner products between my local observables and my MPS. And this from a diagram from the base of products of matrices. And we can it's just a rewriting exercise of seeing this correlation. Again, I think my internet is again, maybe.
You cut out, but then it catches up. So what you said seems to have been, it seems to get recorded and then sped up. So I don't think we're missing.
Okay. Okay, I'm sorry about that. So yeah, I was just saying, so we can rewrite this correlation function not as an inner product, but as a trace of involving some operators A that I've denoted A hat and B hat that you obtain in a very straightforward way from your observables A and B, intertwined with some powers of my transfer operator T. And from this, a consequence of this writing for my correlation function is the following upper bound on this correlation function. So if I denote by lambda 1, lambda 2, etc., the eigenvalues of my transfer operator, so this time with multiplicity, so they are ordered like in decreasing order for their modulus. I denote by delta the spectral gap, so the difference between lambda 1 and lambda 2, and by epsilon the ratio between lambda 2 and lambda 1. And then I have the following upper bound for this correlation function. So some prefactor here that is not really important, that depends on the normalization of T. And then this coefficient epsilon, so this ratio between second largest and largest eigenvalue of T to the power Q times the operator norms of my observables A and B. So this inequality is really showing us that the correlations between my two one-side observables A and B is decaying exponentially with the distance separating the two sites. And the rate of this decay is simply given by the log of this coefficient epsilon. And what people in physics define as being the correlation length in this MPS is simply the inverse of this exponential decay rate. And this correlation, the smaller this ratio epsilon, the smaller this correlation length. And what we see from here is that if you want to estimate this correlation length, then it's really boils down to estimating the largest and second largest eigenvalues of this transfer operator T, which is exactly the same as estimating largest and second largest eigenvalues of the corresponding quantum channel phi T, and which is something that we know very well how to do, as I explained in length in this talk. And for a lot of distributions for my operators K1 to KB, I mean, I can do it. So for instance, if these KIs are renormalized or unitaries, if these KIs are blocks of Haar isometries, if these KIs are renormalized Gaussian matrices, or even more general distributions, then for all these models, we can compute the largest and second largest eigenvalues of the transfer operator and deduce that if the corresponding MPS chi is going to be such that for large n, its correlation length is going to be typically upper bounded by log 1 over log of square root of d, so 2 over log d. So a correlation length that is actually going to be very small if this physical dimension d is large. And with this, I mean, I think I'm really getting to the end of my time. So, I mean, okay, here I had written a few perspectives. So, I mean, some of them I have really already talked about it. So the first one, it's like, okay, what about explicit constructions? And I mean, some steps toward de-randomization and looking at models that involve unitaries. A second one, which is much more of a mathematical question, I don't know if it's interesting from a physical point of view, is to try and identify the full spectral distribution of random quantum channels. Because what we've seen here, that if I have a random quantum channel sampled in a very general way, then if I look at the eigenvalue, my quantum channel 5 minus the in a disk of radius of order 1 over square d for large n. But you can ask, what is this exact radius? What is the exact constant here? And inside this disk are the eigenvalues uniformly distributed. So these kind of questions, like of the full spectral distribution, I mean, has been studied in the classical case quite extensively, and in the quantum case, not at all. So it could be one thing to look at. In the context of NPS, I mean, it would be really interesting to look at models where you impose that actually your cross operators have an additional symmetry. So maybe you sample them at random, but constraining that they are invariant under the action of a group that is actually relevant in your physical model. And you could ask, I mean, do the results about the typical spectral gap remain true in this setting? And then final question would be, I mean, here I've presented to you like one notion of expansion, so this spectral expansion, which is, but there are other ones that you can define. So some more geometric notions of expansion that somehow measure how much uniformly, like how much your quantum channel is uniformly spreading into space. Some more linear algebraic notions of expansion that we look at the span of your cross operators. So you have all the different notions. The spectral expansion is known to be like somehow the strongest of all of them, and it could be interesting to see if you can construct explicitly or at random channel that exhibit maybe this weaker notions of expansion. And with this, I'm gonna thank you for your attention and stop.